Directional solidification and its need in casting. As the molten metal cools and solidifies in the mold, it shrinks or contracts in volume due to varying sections of the cast part and different rates of heat loss to adjoining mold walls. Some portion of the molten metal tends to solidify more quickly, resulting in voids and cavities than other portions. These voids must be filled with the incoming liquid metal from the feeder head riser. Hence, the casting must be so designed with respect to the feeding system such that the part of the mold that is farthest from the feeder head must solidify first and then proceed through the casting towards the feeder head. The solidification which is made to occur in this particular direction is known as directional solidification. Directional solidification can be described as the solidification of molten metal taking place in such a manner that liquid feed metal is always available for that portion of the metal that is just solidifying. It can also be described as the solidification of molten metal taking place progressively from the thinnest part, which solidifies first, and towards the feeder head riser, which solidifies last. Directional solidification and progressive solidification or parallel solidification are the two types of solidification in castings and hence not be confused with each other. Although these processes share some common traits, the difference lies in that in progressive solidification, the cooling and solidifying process begins at the walls of the casting and works its way inward. With directional solidification, the process of solidification begins at the bottom of the casting and works its way to the top. Methods or factors controlling directional solidification. The various methods of directionally solidifying a molten metal and hence to obtain a sound casting is listed and discussed as follows: proper design and positioning of the gates and risers, use of insulating pads and sleeves for risers, use of chills in the mold, incorporating blind riser and use of exothermic riser compounds. Proper design and positioning of the gates and risers. The shape of the riser must be such that it must lose minimum heat keeping the metal in the molten state. This can be met with a spherical shaped riser. However, its incorporation in the mold is difficult. The next best shape is cylinder sand than a square. Cylinder riser is the commonly used and it must be at least 15 to 20% larger in diameter than the section it is required to feed. The riser height is usually 1.5 times greater than its diameter. To increase volume to surface area ratio, the bottom of the cylinder riser can be shaped as hemisphere. The riser must be positioned suitably so that solidification is directional from the casting extremities towards the riser. Use of insulating pads and sleeves for risers. The sides of the riser are insulated with sleeves made from suitable materials so as to achieve lower solidification rate in the riser. This enhances better feeding of the casting. Sleeves made from plaster of Paris are used for non-ferrous castings, while perlite sleeves or fireclay sawdust sleeves are used for ferrous castings. Cellulose materials like rice hulls are also used. Insulating pads can also be employed in various parts of the mold to decrease the cooling rate in thin sections so as to promote directional solidification. Use of chills in the mold. A chill is a metallic object of suitable shape inserted in the sand mold to improve solidification of a region of the casting inaccessible to a riser, thereby promoting directional solidification. A chill will produce local chilling and equalize the rate of solidification throughout the casting. A chill may be classified as internal chill or external chill depending on its location in the mold. Chills placed inside the mold cavity are called internal chills. When the cavity is filled with molten metal, the chill will melt and become part of the casting. Thus, internal chills are made from the same material as the cast part. On the other hand, external chills having high thermal conductivity are placed on the edge of the mold cavity, thereby forming a part of the wall of the mold cavity. External chills are used to increase the feeding distance of a riser or reduce the number of risers. Use of blind riser. A conventional riser is open to atmosphere, whereas a blind riser is completely enclosed in the sand mold. As a result, the molten metal in the blind riser cools slowly and stay liquid longer, thereby promoting directional solidification. Use of exothermic riser compounds. Exothermic riser compounds are loose materials, essentially mixture of a metal oxide, iron, manganese, cobalt, nickel, copper, etc., and aluminum sprinkled on the top of riser in place of insulating powder. Their function is to prevent heat loss from the top of riser and also add some heat to the molten metal in the riser, thereby allowing the metal to stay hotter, necessary for achieving directional solidification.